Welcome to the video lecture on average rates of change. Let's start by talking about the difference between an average rate of change and an instantaneous rate of change. Imagine that you're going on a road trip and your car travels 130 miles in 2 hours. Then your average rate of change would just be the distance that you traveled, which is 130 miles, divided by the time that it took you to travel that. So 2 hours. So 130 divided by 2 gives us 65 miles per hour. So that's our average speed over the course of the entire journey. Now if we contrast that with our instantaneous rate of change, that would not be your average over the entire trip. It would be if you were to look down at your dashboard and notice how fast you were going at one specific moment in time. So if you look at your speedometer at exactly one moment in time and see that you're going 72 miles per hour, then at that moment, that's your instantaneous rate of change. So your instantaneous rate of change, for example, 72 miles per hour, is how fast you are going at one moment in time. Whereas an average rate of change is how fast you're going over a whole interval of time, in this case from 0 to 2 hours. This particular lecture is going to focus just on average rates of change. So let's take a look at this graph. This graph represents the total number of words, m of t, that a person can memorize in time t, where t is in minutes. And it's shown in this graph. So for example, this point 16, 20 means in 16 minutes I can memorize 20 words. Okay? So what we're going to do is use this data to find the average rate of change of m as t changes over various intervals. Now keep in mind that an average rate of change requires an interval of values. So you need to know when you're supposed to start counting and when you're supposed to stop counting. So you need a start and a finish time. So let's make a little definition here. We're going to say that the average rate of change for this particular problem is the change in the number of words memorized over the change in the time. This is exactly what slope is. It's like change in y over change in x. But in this particular example, we don't have y's and x's, we have m's and t's. So we're going to find these average rates of change exactly like we would find slopes. So if we're looking at an interval of time from t1 to t2, and that corresponds to an m1 and an m2, then our average rate of change would be m sub 2 minus m sub 1 over t sub 2 minus t sub 1. And it doesn't really matter which order you subtract, as long as you're consistent on the top and the bottom. So if you start with time 2 on the bottom, you need to start with m2 on the top. So for example, if we wanted to find the average rate of change over the intervals 0 to 8, t sub 1 is our 0, t sub 2 is our 8. So our average rate of change would be the change in the m's that correspond to these t's over the change in the times. So at time 0, we're right here on our graph, so obviously we've memorized 0 words, but at time 8, we've memorized 10 words. That's this point 8, 10. So our m sub 2 would be the 10, and our m sub 1 would be the 0. Our t sub 2 would be the 8, and our t sub 1 would be the 0. So if we simplify that, we get 10 over 8, and if we divide by 2, we're going to get 5/4, or as a decimal, 1.25. Now let's think about what the units on this average rate of change would be. Since we're calculating our average rate of change using change in m over change in t, m is number of words being memorized, and t is time. So if we put our units on our answer here, 1.25 means the number of words that I can memorize per time, and in this case our time was being measured in minutes. So what I like to do is I put this over a 1 so that I can kind of say it out loud to myself, and this represents that I can memorize 1.25 words per minute. So that's the representation, or that's the meaning of this average rate of change in the context of this question. Okay, let's try the next one. This time our t is starting at 8 and going up to 16. So our t sub 1 is 8 and our t sub 2 is 16. T sub 1 of 8 seconds again corresponded to 10 words, and 16 seconds corresponds to 20 words. So our average rate of change is going to be the 20 minus the 10, the two m's subtracted, divided by the two t's subtracted, 16 minus 8. So 20 minus 10 is 10, 16 minus 8 is 8, and so we get 5/4 again, or 1.25 words per minute. So same exact value as the last example. If we try the next one, now we're going to look at a T1 of 16 and a T2 of 24. When the time is 16 seconds, our number of words was 20, and when the time is 24 seconds, our number of words is 25. So our average rate of change will be the two m's down here at the bottom subtracted, so 25 minus 20 over our two t's subtracted, so 24 minus 16. So that's going to give me 5 on top and 8 on the bottom. So as a decimal, that's 0.625 words per minute. If we go to the next example, now our T1 is 24 minutes and our T2 is 32. So when the time was 24, our number of words was 25, and when our time is 32 minutes, our number of words is also 25. So our average rate of change will be these two m's subtracted, so 25 minus 25 over 32 minus 24, our two t's subtracted. Obviously the numerator there is going to be 0 over 8, so this is going to be 0 words per minute. And if we do our last interval here, our T1 is 32, our T2 is 36. At 32, I memorized 25 words, and at 36 minutes, I also memorized 25 words. So our average rate of change will be these two 25s subtracted over the two t's subtracted. So again, we're going to get 0 on top, 4 on the bottom, so this is 0 words per minute. You can see that as the graph continues, this graph tends to flatten out. We can see that representing itself in the fact that as we progressed, as these times got longer and longer, the average rate of change became 0, and it continues to be 0 from this point on because the times are horizontal. The number of words stays horizontal at 25 words as the time progresses. What would be the significance of that? So what happens to the average rate of change after 24 minutes and why? So how come after this point right here, after we become horizontal, what's happening to that average rate of change? Well, since these y values, these number of words memorized, is staying flat at 25, then our average rate of change between any two of these points will always be 0 on top. And we saw that here and here. Why would that make sense in the context of the problem? Well, the average rate of change is going to 0 because as time progresses, you've exceeded your short-term memory. That's what we're talking about here. We're talking about how many things you can memorize. So after a certain time, you're going to start to forget. So as the average rate of change goes to 0 because you have exceeded your short-term memory. So after 24 minutes, we start to lose our memory and we can't remember as many words because the time is too long. Okay? So average rate of change, just like slope, if we look at For example, this average rate of change of 1.25 words per minute over the interval 8 to 16 minutes, this average rate of change that we calculated, 1.25, corresponds to the slope between these 2 points, right here and right here. And that is called a secant line, a line that goes through any 2 points on your curve. So the slope of that secant line happens to be the same as this average rate of change, this 1.25 words per minute. So we're going to talk some more about that. Now what we're going to do next is we're going to try and formalize this idea of average rate of change. So suppose that you're given any function f of x, and we want to find the average rate of change of y with respect to x between the points p, comma x sub 1, f of x sub 1, and q, x sub 2, comma f of x sub 2. So for example, suppose we have any function, and here's point p, which is x sub 1, comma f of x sub 1, and then q, which is x sub 2, comma f of x sub 2. And we want to find the average rate of change between those 2 points. Well, the average rate of change, as we just mentioned, is exactly the same as the slope between these 2 points, P and Q. So imagine this line right here. This is called your secant line between P and Q. So it's the slope of this secant line. Now, how do you calculate the slope of a line? Well, you do change in y over change in x, and the y values of these 2 points are these 2 function values. So we're going to take this y value minus this y value. So f of x sub 2 minus f of x sub 1, and we're going to divide that by this x value minus this x value. So x sub 2 minus x sub 1. You could also see this written as y2 minus y1 over x2 minus x1. It just depends on whether you're using x's and y's or x's and f of x's. So this is by definition our average rate of change between any 2 points on a function. Okay, so let's write it right here just to have it in a nice spot. So it's the change in the function values, the difference in the f's or the y's, divided by the difference in the x's, or the difference in the y's over the difference in the x's. You want to have this memorized. Okay, this is the definition of the average rate of change. Now, as we mentioned before, the line between these 2 points, P and Q, is called the secant line. So you'll also want to have that terminology memorized as well. So suppose that we have a function f of x that's equal to x squared plus x, and we want to find the average rate of change as x changes from 1 to 2, from 1 to 3, and from 2 to 3. So we're just going to use our formula up here to figure that out. So suppose we want to look at it as x changes from 1 to 2. Sometimes we'll write that as an interval, where these are the x values from 1 up to 2. I'm going to use an interval notation. So this would be my x sub 1, and this would be my x sub 2. So by definition, this average rate of change is going to be the function value at 2 minus the function value at 1 divided by the x sub 2, which is 2, minus the x sub 1, which was 1. So let's figure out what some of these function values are. How do I find out what f of 2 is? Well, here's our function right here. So f of 2 is going to be, and I'm just going to plug in 2 for x. This would be 2 squared plus 2, which is 4 plus 2, or 6. So f of 2 will be replaced with a 6. Now let's find f of 1. So I go back to my function, and this time I'm going to plug in 1. So 1 squared plus 1 is just going to be 2. So you just find these f values by plugging the x's into your function. So if we simplify that, we're going to get 4 on the bottom, or 4 on the top and 1 on the bottom, so our final answer is 4. Okay? Let's try it again, but this time we're going to look at the interval from 1 to 3. So this time our x sub 1 is 1 and our x sub 2 is 3. So our average rate of change will be the function value at 3 minus the function value at 1 divided by 3 minus 1. Now just a side note here, it would also be correct to do f of 1 minus f of 3 over 1 minus 3. You can do the order in either direction. Since we're typically thinking of these as times, not always, but sometimes I usually do the larger value minus the smaller value. Okay? So how do we find these function values again? Well, we just go to our function f and plug in. So we need to find out what f of 3 is. So I'm going to plug in 3 for these x's. So 3 squared plus 3, that's going to be 9 plus 3 or 12. So f of 3 is 12. F of 1, we already figured that out, that was 2. So on the top we're going to get 10, on the bottom we're going to get 2, so this reduces to 5. Alright, if we try one more, this time we're going to look at the interval from 2 to 3. So my x sub 1 is 2 and my x sub 2 is 3. And my average rate of change by definition is f of 3 minus f of 2 over 3 minus 2. So f of 3 we already calculated, that was 12. F of 2 we already calculated was 6. So we're going to get 6 on the top, 1 on the bottom, and the answer is 6. Okay? All right. Next question. Suppose that f of x equals to 2x plus 3. What is the average rate of change over any interval? So this one is not giving me an x sub 1 and an x sub 2. It's just asking for the average rate of change over every interval. Now let's see if we can figure this out. Let's look at a graph of this function. Because this is a linear function, because it's x to the first, we know how to graph this. This has a y-intercept at 3 because that's our b, and then our slope is 2 over 1. So I'm going to rise up 2 and I'm going to go over 1. So my graph is going to look just like this. Now remember what we said. Average rate of change corresponds to the slope of the secant line between our 2 points. So let's take a look at 2 random points. Let's say that I pick this point here and this point here. What's the slope between those 2 points? Well, I'm going up 2 and over 1. So my slope between those 2 points is 2. Now what's going to be my slope if I had picked 2 different points, say here and here? Well, the good news is, since this is a line, lines have constant slope. So no matter which 2 points I look at, whether it's way out here or 2 points closer together, the ratio of this rise to this run is always the same value, and it has to always be 2. So the slope is 2 for every pair of points, which means the slope is going to be 2 for every interval, and that's because it is a linear function. So when you have a linear function, your average rate of change is always going to be just whatever the slope of that line happens to be, because the slope is constant no matter which 2 points we look at. So we've talked about how to find the average rate of change by just calculating the slope between our 2 points. We're going to do that again in an alternative notation. So instead of thinking of our 2 points P and Q as x sub 1, y sub 1, and x sub 2, y sub 2, this time we're going to think of our points P and Q as x comma f of x for our P. And this time we're going to define Q a little bit differently. We're going to say that Q is x plus delta x comma f of x plus delta x. So here's the idea. You're going to have some general function f, and you're going to pick sort of a starting point. That's going to be our point P, which has coordinates x comma f of x. And then a lot of times in calculus, what we want to do is we want to go just a little distance away from that base point. And so what we're going to do is we're going to define our point Q to be just a little distance away from X. So it's still going to be close to X, but it's going to be just a little bit more than that. So we're going to pick this delta X to usually be something really, really small, like 0.01 or 0.001. So X plus delta X would just be a little bit away, and our point Q would therefore be very close to point P. So these P's and Q's are really close together. Now if we define our 2 points in this way, then let's talk about what the average rate of change between these 2 points would be. Well, it's still going to be the slope of this secant line. Okay, that's not changing. So our average rate of change will be the slope of the secant line between P and Q. So how do you find that slope of that secant line? Well, that's just the change in the y values over the change in the x values. So the change in the y's are going to be the y value of Q, which is this f of x plus delta x, minus the y value of P, which is our f of x. And then on the bottom, we're going to do the difference in our x's. So the x value of our Q is x plus delta x, and then we're going to subtract from that the x value of our P, which is just x. And what you'll notice on the bottom there is that these two x's cancel, and what we end up with is this expression, f of x plus delta x minus f of x all over delta x. And this is going to be our average rate of change, and it also has another name to it. It is called a difference quotient. And difference means subtraction, and quotient means division. So we have our subtraction right here, and then we have our division right there. So that's why it's called a difference quotient. So the difference quotient is going to be f of x plus delta x minus f of x all over delta x. And you'll probably want to have that memorized because a lot of problems are going to ask you to find a simplified difference quotient. So you need to know what this formula is to figure out what your difference quotient should be, and then we'll simplify it from there. So let's see some examples. Let's start with that function x squared plus x that we were working with earlier, and we want to find the difference quotient when x equals 1 and delta x equals 1, and then we're going to find the other difference quotient when x equals 1 and delta x equals 0.1. So we're going to let x equal to 1 and delta x equal to 1, and then we're going to do it again and let x be 1 and delta x equal to 0.1. So to find our difference quotient, we need to use our difference quotient formula, which is f of x plus delta x minus f of x all over delta x. So let's plug in what our x is and our delta x is. X is 1 and delta x is 1. X was 1, so I'm going to put a 1 there, and our delta x on the bottom is also going to be a 1. So what this simplifies to is really f of 2 minus f of 1 all divided by 1, which we don't even need to write. So what is f of 2 again? Well, to get f of 2, you plug in 2 for x. So that's going to be 2 squared plus 2. 4 plus 2 is 6. And f of 1, we're going to plug in 1 for x, so that would be 1 squared plus 1, which is just 2. So this is going to give me a difference quotient of 4. Okay, so let's try this again with a different delta x value. So we're still using this same formula, f of x plus delta x minus f of x all over delta x, but this time we're plugging in different values. So this time our x is 1 and our delta x is 0.1, and I'm going to use x equals to 1 in this part as well, and our delta x is 0.1. So we need f of 1.1 minus f of 1 all over 0.1. So we need to figure out what f of 1.1 is, which would be 1.1 squared plus 1.1. And you can punch that into a calculator, and you're going to get 2.31 when you plug that in. So this is 2.31 minus f of 1. F of 1 was 2. We had that earlier up here. So we're going to get 0.31 divided by 0.1, which turns this into 3.1. So there's our difference quotient for those two values. Now what if I asked you to find several difference quotients for this same function, but for different values of delta x? So say I wanted to find the difference quotient when x was 1, but when delta x was 0.1, 0.01, 0.0001, and so forth. It's going to get pretty tedious to have to redo these calculations every single time for a different delta x. So I'm going to show you an alternative way to do this problem so that instead you leave your answer for your difference quotient in terms of x and delta x. You use the function's formula and substitute in, but then at the very end you can plug in what your different x or delta x values are, so that you're really only doing the work of the difference quotient once and then just plugging in different x's and delta x values at the end, instead of having to do the difference quotient 2 or 3 or 4 different times. So it's supposed to be a time saver. So here's what we would do. What we could do is we could take our function, which was x squared plus x, and we could write out what the general average rate of change or difference quotient would be for this function. So that formula was f of x plus delta x minus f of x all over delta x. But what I'm going to do differently this time is I'm not going to plug in an actual number for x or delta x. I'm going to figure out what this is in terms of my variables. So we need to figure out what f of x plus delta x would be. How would you figure out what that is? Well, remember when we wanted to find out what these f values were up here, like f of 2 or f of 1.1, we just took whatever number we saw inside here and we substituted it in for these x values. So that's what we're going to do here as well. So I'm going to take this x value right here and replace it with this whole input, x plus delta x. And that x was supposed to be squared, and then we need to add to that an x again, but this time my x isn't just x, my x is this whole expression, x plus delta x. So this is what we would get by plugging in x plus delta x in for our input. If it helps, you can think of this function instead of as f of x, you can think of it as f of stuff. And the rule for this function is whatever that stuff is squared plus that stuff again. And that's what I did here. Here's my stuff squared, and here's my stuff added on to the end. Okay? So I'm just replacing that box with x plus delta x. Alright, now we're not quite done. That is just this piece right here. We still need to find out what just plain old f of x would be. And f of x would be the same rule, but with x's plugged in to these boxes. So that's x squared plus x. That's the normal rule that you would normally use for just f of x, right? So we need to be a little bit careful here, because what do we want to do with these two function values here? We want to subtract them. So don't just put a minus sign here, because all of these terms represent f of x, so you need to use parentheses around them to subtract both of these from all of this f of x plus delta x stuff. So here was my f of x plus delta x, here was my f of x, and I subtracted them. And what are we supposed to do with that difference? We have to divide it by our quotient delta x. So this is what it looks like initially, and it looks like it's pretty messy, but we're going to simplify it. So we're just going to do a little bit of arithmetic here. I'm going to start by FOILing out this quantity. And remember, when you FOIL, you're going to get a middle term. We're going to get an x squared. Our middle term would be an x times a delta x, but I'm going to get two of those. So I'll get a 2x delta x, and then I'm going to get a delta x squared. Now, if you're not sure where I'm getting that from, that's just x plus delta x times x plus delta x, and all I'm doing is FOILing. And that's where these terms come from. Okay? Then I have these two terms as well. And then I need to distribute my negative across. And all of that is over delta x. Now, if we're doing this correctly, a couple things should cancel out. I have that my x squares cancel and my x cancels. And so what I'm left with is 2x delta x on top plus a delta x squared on top, and then I have another delta x right here as well. Now, one last thing I'm going to do, notice that every term in the top has a delta x in it. So let's factor out that delta x from the numerator. That would leave me with a 2x plus a delta x plus a 1. And the reason I want to factor out that delta x is because I also have a delta x in the bottom. So I'm going to cancel those two guys out. You should always be able to cancel out that delta x when you're simplifying these difference quotients. If for some reason they aren't canceling out, then your arithmetic up here must have been wrong. You made a mistake somewhere. So our final answer would be 2x plus delta x plus 1. And this is called our simplified difference quotient. Now, that was a little bit of work to do all that, but the idea here is when you do that, you're doing this work exactly once, and then what I could say from this point is now use this as a formula, and you could calculate many different difference quotients by just plugging in your different x's and your different delta x's into this formula. So for example, I could plug in 1 for x and 1 for delta x, and I should be getting 4 for an answer. Or I could plug in 1 for x and 0.1 for delta x, and I should be getting 3.1 for an answer. So it saves you a little bit of work in terms of the actual difference quotient if you have many different x's and delta x values to substitute in. Now, the question might also be worded where they don't give you a specific x and delta x to plug in at all. They might just say, find the simplified difference quotient, which means you have to go through all of this algebra that we just did, and your final answer will be a formula like we got on this last example, this 2x plus delta x plus 1. So let's try this again for the function 5x cubed. So to find our simplified difference quotient, we start with our definition, our formula. The formula for a difference quotient is always f of x plus delta x minus f of x all over delta x. This time what's different is my function. So this time my function is f of stuff is 5 times that stuff cubed. So for this first expression here, this is my stuff, x plus delta x. So we're going to put in this box x plus delta x wrapped in parentheses. So f of x plus delta x should be 5 times this x plus delta x quantity cubed. That's what it becomes. That's the tricky part. That's the part that students mess up on, is not substituting in correctly into the function. Now, what is f of x? Well, this time my stuff is just x. So I'm just going to put an x in that box. So it's just going to stay plain old 5x cubed. Okay? On the bottom, don't forget, we're dividing that by delta x. So now what we're going to do is we're going to have to simplify this. It says to simplify, and you know that you're not done until you've done your very last step, which should be to always cancel those delta x's on the top and the bottom. That should be your last step. So we need to work our way towards that step. And when I see something like this, the only thing I really can do is FOIL out this x plus delta x cubed. Now there is a formula for how to cube a binomial, and this is something you would have learned in intermediate algebra, and hopefully you have it memorized, because if you don't, then you're forced to do all of this foiling 3 times, which is tedious to do, but it's certainly doable. Instead, I have this formula memorized. What I know is that when I cube a binomial, it's always this first term cubed, and on the end this last term cubed, and then I have 2 middle terms. The first middle term has 2 x's and a delta x, and the second middle term has 1 x and 2 delta x's, and both of those middle terms have coefficients of 3. If you look at the degrees, the x is cubed, then squared, then 1, and then 0. And on the delta x's, I have 0 here, 1 here, 2 here, and 3 here. So when I cube this out, I'm going to get an x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. And then what I want to do to all of that is distribute my 5. So I'm going to get 5x cubed plus 15x squared delta x plus 15x delta x squared plus 5 delta x cubed minus that 5x cubed from the side. And what's good is that those 5x cubes should cancel. So what we're left with are just terms on the top that have delta x's, which means I can factor out a delta x from each of these 3 terms. You could pull out more than just a delta x. You could pull out a 5 as well, but I'm not going to bother because it's only the delta x that I know I'm going to be canceling with on the bottom. So I'm going to leave the factor of 5 inside my parentheses. So I'll have 15x squared from the first term plus 15x delta x from the second term plus 5 delta x squared from the third term. And I know I'm good when I see those delta x's canceling, and my leftovers is my final answer. So 15x squared plus 15x delta x plus 5 delta x squared is what we call our simplified difference quotient. And you're going to be seeing this again in the next chapter when we talk about the derivative, which is a very, very important concept in calculus. And this difference quotient has huge impact in determining what that derivative is going to be. So this is something you're going to see again and again and again. Alright, let's try one more example just like that, but with a different function. So here we want to find the simplified difference quotient for the function 4 over x. So if you want to think of this function as f of stuff, and its rule is 4 over whatever that stuff happens to be. Okay, so let's start with our formula for our difference quotient. It's always going to be f of x plus delta x minus f of x all over delta x. And in this problem, this is our stuff. So for f of x plus delta x, I want to do 4 over that stuff. So 4 over x plus delta x. Now when I go to my second function, we're going to subtract it. This time my stuff is just an x. So I want to do 4 over my stuff, or 4 over x. And all of that gets divided by delta x. Now what we've just created is called a complex fraction. It's a fraction within a fraction. So to clean it up, the easiest way to do that is to multiply this by a fancy version of 1. And what we're going to multiply by is the common denominator of these 2 fractions on top over that same common denominator. And since these 2 denominators are different, my common denominator should just be the two of them multiplied together. So I need an x and I need an x plus delta x. I need one of each. So we're going to multiply the top by that as well as the bottom, so that we're not changing our problem at all. We're just multiplying by a fancy version of 1 here, so that we're staying equivalent to what we started with. Now, why does this help us? Well, when I multiply this fraction times my common denominator, this denominator cancels out this factor and leaves me with just this 4 and this x. So I'm left with 4x. Now if I do that again for the second fraction and multiply this by my common denominator, this time the x's cancel and I'm left with my 4 and this stuff in parentheses. And we're subtracting that. Now on the bottom, we don't have a fraction with a denominator, so nothing cancels out. And I would recommend that you do not FOIL or distribute across the bottom. Instead, just take this, this, and this and push them all together. And it doesn't really matter in what order you put them in. It's up to you. So now what we're going to do is we're just going to clean up the numerator a little bit by distributing this negative 4 across. So I have my 4x from here minus 4x from here minus 4 delta x when I distribute. What is good about that is my 4x's on top cancel out, and that means we're left with negative 4 delta x over delta x times x plus delta x. And this is why I recommended that you didn't distribute on the bottom, because this delta x here should cancel with that one. And remember, that's always your last step when you divide out and cancel out those delta x's. So what we're left with is minus 4 on the top over our x parentheses x plus delta x. And that is called our simplified difference quotient. Okay? So we're going to finish off with one application here. Oops. Our application is dealing with an object in free fall. So just imagine going up to a really tall building and having a ball in your hand and just letting it go and letting it fall to the ground. That's free fall. So that object, that ball, is being acted on by gravity to pull it down to the ground. And what we know from physics is that an object in free fall will fall a distance s. Usually in science or physics, distance is used or is measured with this s variable, and it's measured with a distance s in feet in t seconds by this formula. So this is coming from physics. You don't need to know where it is derived from or how it comes about, but it's based on that acceleration due to gravity. This 16 is half the acceleration due to gravity in feet per second squared. So this is our distance of the object falling in t seconds. So question A, how far does the object fall in 2 seconds? So 2 seconds is a time, that's a t. So this is just asking, if t is 2, what is the distance traveled, or what's the distance that the object has fallen? And that's exactly what this s is. So all we have to do is plug in 2 for t, and that should calculate for us how far the object has fallen. So 16 times 2 squared. 2 squared is 4. 4 times 16 is 64. And remember, distance was being measured in feet. So our object has fallen 64 feet. Okay? So question B, how far does the object fall in 4 seconds? So this time our time t is 4, and we're looking to find s of 4. So 16 times 4 squared. 4 squared is 16. 16 times 16 is 256 feet. So this time, after 4 seconds, now we've fallen 256 feet. Part C, what is the average rate of change of the distance with respect to time during the interval 2 to 4 seconds? So starting at 2 seconds and going up to 4 seconds. So this is your T1 and your T2, and we're trying to find an average rate of change. So this is exactly what we did at the beginning of this lecture. But this time, instead of talking about words per minute, this time we're talking about distance per time. So instead of M's and T's, this time we have S's and T's. So if you will, this formula for average rate of change is change in position or change in distance over change in time. So what we need to do is find the two distances that correspond to these two times, and we're going to subtract them to find that change in distance. So we would want to know the position or the distance after 4 seconds minus the distance fallen after 2 seconds, and then we'd want to divide that by the difference in the two times, 4 minus 2. Now luckily in part A, we found S of 2 already. That was this 64. And in part B, we found S of 4. So that was this 256. So we already got those two values from our function. 256 minus 64 is 192. 4 minus 2 is 2, and when I divide, I get 96. Now what kind of units should be on this? The units come from the units of our average rate of change. And remember, on top, these were distances which were being measured in feet, and on the bottom were times which were being measured in seconds. So the units that make sense here would be feet per second. So if you think about what this means in the context of the problem, this means that our object has fallen an average rate of change of 96 feet per second. And in physics, this has another name. Instead of calling it an average rate of change of distance with respect to time, that gets a little bit lengthy to say, we just call that average velocity. So average velocity of this object is 96 feet per second. It was how fast the object fell over the time interval 2 to 4 seconds. So it's like a speed, it's a velocity, but it's over an interval of time. So by definition, average velocity is going to be change in distance, which we sometimes just write as change in S, or S of T2 minus T1 over our change in time. So that's change in T or T2 minus T1. So you want to have that memorized as well. It's exactly the same thing as average rate of change or slope of a secant line, but it's in the context of a function that's measuring distance over time. So average velocity, how fast an object is traveling over an interval of time. All right, that concludes our lecture on average rates of change. Good luck.